Hello. You've all been aware of the current structure of the atom. You've been taught in chemistry with a nucleus at the center and electrons orbiting on the outside. That hasn't always been the best known model of the atom. Previously, before that, was one called the plum pudding model, which you can read about in your notes. It basically consisted of a, uh, a sphere of positive charge with electrons distributed throughout it. Electrons have been discovered already. Overall, the atom was neutral, and that was the best known model. However, at the start of the last century, there were experiments done by Ernest Rutherford and his assistants Geiger, and they used something called alpha particles, that we'll look at in a later part of the topic, to try to probe matter. And they set up an experiment that was similar to what you see on the screen, but a little bit different. They had a source of these alpha particles, and they fired them out at a very, very thin sheet of gold foil, a few atoms thick. And um, they used a fluorescent screen. In this case, it looks like a fluorescent screen that wraps the whole way around, but they used a smaller one that they moved around. And whenever an alpha particle struck the screen, it would give off a tiny flash of light. And so Geiger and Marsden, assistants, sat in darkened rooms for hours at a time, looking to see where alpha particles hit the screen. The vast majority of them went straight through, but a very small number were deflected a little bit to the side, and a very tiny number, about 1 in 8,000, were deflected right back, backscattered. And this surprised them, because they were expecting the particles just to move straight through. How could an alpha particle, which is known to have a bit of mass, and it was known to be positively charged, how could it be bounced right back? So what we saw was the alpha particles, the vast majority just went straight through. A very small number deflected back. And there were a few that were scattered. And eventually they came to the conclusion that most of the atom must be made of empty space, which allowed the particles to move straight on through. But there must be mass in the atom, because everything has mass. They decided that the mass must be concentrated in a very small part at the center of the atom. And this is called the nucleus. So it has to be very small, it has to be very dense, and have most of the mass of the atom. And because it deflected, it repelled these positively charged alpha particles, it must also be positively charged. This is where the idea of the nucleus came from. So most alpha particles passed straight through. What did that mean? That most of the atom was empty space. Some were deflected, meant that there had to be a small, dense, positively charged nucleus. And because the atom was neutral, it meant that the negative electrons were orbiting the nucleus, a bit like a solar system. Okay, so we've ended up with this model of the Rutherford bohr atom, the atom that you all know. At the center, we have protons and neutrons. They weren't discovered later, and we don't need to know how they were discovered, but again, it was by firing particles and things. We'd call that the nucleus. Orbiting the nucleus with the electrons. But the scale of this is not something that we can really show in a diagram. So nucleus is incredibly small, about 1/1000,000 of a billionth of a meter across, roughly. But the overall atom is about 100,000 times bigger than that. So it's a huge difference in scale. Standard sort of description is like if the atom was the size of a football pitch, the electrons going around the outside, the nucleus would be about the size of a pea at the center of the football pitch. So most of the atom, all the region around the nucleus, between the nucleus and the electron, is empty, has absolutely nothing in it. Now, we also know that the electrons are very much lighter than the protons and the neutrons. This is all stuff that should be familiar to you. We know that the proton and the neutron have a relative mass of about 1, whereas an electron is we're going to say 1 over 1,840. So about 1/2000th of the mass of a proton or neutron. So all the mass of an atom is really contained in the protons and neutrons, electrons, and some tiny, tiny, tiny fraction. Which means that all the mass is contained in the nucleus. It's very dense. It must be a very, very dense nucleus. Huge amount of the volume of the atom is nothing. There's no mass at all. We also know that the charge of the proton and the charge of the electron are equal but opposite, which is why we have a neutral atom. A neutral atom has the same number of protons and electrons. Neutrons do not contribute to the overall charge of the atom. These masses and charges are not using any particular units. They're just in comparison with the proton. The mass of a proton is about 1.67 times 10 to the negative 27 kilograms. And its charge is 1.6 times 10 to the negative 19 coulombs. Those are numbers you don't need to worry about, but we'll maybe mention at a later stage.